When astronomers pointed two of Earth's most powerful observational tools, I mean, we're talking the Chandra X-ray Observatory and the massive Keck telescope here, when they pointed them at a tiny speck of light called a green pea, they really just expected to find, a local oddity.
Yeah, just a weird little local galaxy.
Right. But instead, they found two monstrous black holes staring back.
Ugh.
So, welcome to this deep dive. Our mission today for you is to unravel this cosmic mystery.
It really is a mystery, too.
It totally is. We are going to connect a bizarrely named modern galaxy to the very dawn of time. And well, in the process, we're going to try to figure out how the universe's most massive black holes managed to grow up so incredibly fast.
Yeah, it's a phenomenal astronomical detective story, really. We're looking at this amazing convergence of data from entirely different telescopes and, entirely different epochs of the universe.
Oh, wow.
And it's all pointing toward the same underlying physical truth about how galaxies and their black holes actually evolve together.
Yeah, and we have some amazing sources driving today's exploration. We're looking at a brand new preprint about this Green Pea object, plus a foundational 2018 Nature study on hidden galaxy crashes, and this cutting-edge 2026 Nature paper trying to make sense of the James Webb Space Telescope's most puzzling recent discoveries.
Right, the JWST data has really thrown a wrench into things lately.
Oh, completely. So let's start with the scene of the crime. The target bears the incredibly catchy name SDSS J1622 around 9.41 plus 352 knows 87.5.
Rolls right off the tongue.
Doesn't it? But it's classified as a green pea galaxy. And just to playfully clarify for you listening, we're not talking about a rogue vegetable floating through the cosmos.
No, definitely not. Far from it. Green peas are this very specific, rare class of compact galaxies, and they were originally flagged by citizen scientists, actually.
We really like everyday people?
Yeah, exactly. Everyday people volunteering for the Galaxy Zoo project. They were just clicking through millions of images from the Sloan Digital Sky Survey, and they started noticing these tiny, unresolved green dots.
That is so cool. So where does the green come from?
Well, the vibrant green color actually comes from intensely glowing, doubly ionized oxygen. They're extremely compact and they have very low metallicity, which just means they are fundamentally lacking in elements heavier than helium. Plus, they are undergoing this explosive runaway star formation.
Right. And crucially for our purposes today, green peas act a lot like local time machines. Because, they're so compact, metal poor, and bursting with new stars, they strongly resemble the rapidly assembling galaxies that we usually only find way back in the young universe.
Right, near cosmic dawn.
Exactly. But this particular green pea, SDSS J1622, it had a massive surprise hiding inside its vibrant glowing gas. When astronomers looked at it with Chandra, they didn't just see one luminous hard X-ray source. They saw two.
Yeah, and the absolute clarity of that observation is really what sets us apart. I mean, Chandra resolved two distinct, extremely luminous hard X-ray sources inside this one tiny galaxy.
This is wild.
It is. And then researchers followed up with optical spectroscopy from the Keck telescope in Hawaii, which confirmed that both of these sources sit at the exact same redshift.
Okay, so just to be clear, that means they're at the exact same distance from us, right?
Yeah, exactly. They are moving together through space, so it's not some optical illusion where a foreground object just happens to perfectly align with a background object.
Okay, got it.
We are looking at two actively feeding supermassive black holes, and they're separated by about 8.4 kiloparsecs, which is actually relatively close in galactic terms.
And they're huge, right? Like 10 to the 7.3 solar masses each.
Yeah, which means each one is roughly 20 million times the mass of our sun, and they are both efficiently eating the surrounding gas and dust.
20 million suns. That's just hard to wrap your head around.
It really is. And just to set the stakes and clarify the terminology here, astronomers call this a dual active galactic nucleus, or dual AGN. It is a pre-coalescence snapshot.
Meaning they haven't merged yet.
Right. They are not yet a tight, close binary system. And they aren't going to collide tomorrow. We're catching them in the early stages of an unfolding cosmic dance, basically just approaching each other as their host galaxies merge.
Okay, let's unpack this. Because if I'm looking at a messy galaxy collision, my first thought isn't necessarily, hidden black holes.
Sure, yeah.
I mean, a galaxy merger triggers massive shock waves that compress gas and ignite intense starbursts.
Yeah.
Millions of hot young stars are being born all at once. So how do astronomers know for sure these are two black holes? Why couldn't this just be a massive burst of star formation or some weird trick of the light?
Well, we rule it out by acting like detectives, building a case from independent clues. So first we look at the X-rays. In these chaotic merging systems, cold gas and thick dust obscure almost all of the optical light coming from the galactic center. But hard X-rays is extremely high-energy radiation that pierces right through the dust veil. Now, star formation does create some X-rays, but seeing two distinct, incredibly luminous points of hard X-ray emission, that is a massive red flag that you have two hidden accretion disks.
Oh, I see. It's kind of like getting a cosmic dental X-ray. You can't see the cavity from the outside because of the enamel, but the high-energy X-ray exposes the decay hidden underneath.
That's a great way to put it.
But the X-rays weren't the only clue, right? Keck looked at the optical light and saw broad hydrogen lines and highly ionized atoms, specifically neon V and iron 7th.
Hmm.
And I have to ask, what does highly ionized actually mean in this context?
Ah, right. So it means electrons have been violently stripped away from the atom. To create iron 7th, for instance, you have to strip 6 electrons off an iron atom.
Wow.
Yeah, and doing that requires photons packing a tremendous amount of energy, around 100 electron volts.
Okay, so it takes immense energy. But couldn't a really big star do that?
Actually, no. Even the most extreme, massive O-type stars in a stellar nursery cap out far below that energy threshold, they simply cannot throw off radiation hard enough to strip 6 electrons from iron.
Oh, wow. So stars are completely ruled out.
Exactly. The only engine in town capable of generating that kind of fierce, hard radiation is the superheated accretion disk swirling around a supermassive black hole. The diagnostic line ratios of these elements plot these objects firmly in the active galactic nucleus regime. It's a chemical signature that unequivocally points to black holes.
That is fascinating. Plus, we have the larger visuals, right? The optical images show these faint, wispy trails of stars called tidal debris, which indicates these two galaxies are clearly in the middle of a merger.
They are, though we do need to preserve some scientific caution here. Sometimes powerful gas outflows from a single black hole can create double-peaked emission lines that masquerade as two black holes, at least if you only look at the spectra.
Ah, tricky. But in this case, the spatial separation in the X-rays gives us much higher confidence, right?
It does, yeah. But it is also worth noting that this specific Green Pea study is a preprint. It hasn't fully cleared peer review yet, meaning the precise mass estimates and the calculations of exactly how much dust is obscuring these black holes, well, they might shift a bit as more scientists scrutinize the raw data.
Fair enough. So we know dust hides feeding black holes in our local universe. But this naturally brings up a profound physical question for me. Why do these galaxy crashes seem to wake up black holes in the first place? Galaxies are mostly empty space, so it's not like they just bump into each other and all the gas immediately falls straight down into the center.
No, it's not that direct. And this brings in that 2018 study in the journal Nature by Koss and colleagues. They looked at accreting black holes in hidden mergers to figure this out.
What do they do differently?
Well, they used hard X-rays from the Swift satellite to pierce the dust and find actively feeding black holes, and then they followed up with incredibly sharp near-infrared imaging using the Hubble Space Telescope. What they found were nuclear mergers galaxies in the very late stages of colliding that ordinary optical pictures completely missed.
And the numbers there lay out a pretty dramatic contrast, right?
Oh, absolutely. They found that close mergers appeared in a whopping 17.6% of luminous, obscured active galaxies. But when they looked at a matched sample of inactive galaxies, ones with sleeping black holes, they found close mergers in only 1.1% of them.
1.1% versus 17.6%. That is a massive leap.
Yeah, it proves that late-stage galaxy mergers and luminous, obscured black hole growth are intimately linked.
Let's visualize how this mechanism actually works. How a merger forces that gas to feed the black hole. Think of water swirling down a drain, or maybe a spinning ice skater. As long as the skater has her arms out, she spins at a certain speed. She has all this angular momentum, but the second she pulls her arms in, she spins wildly out of control toward the center.
Right. The galaxy merger is what pulls the arms in. When two gas-rich galaxies get close, the extreme gravitational tidal forces between them create a massive torque. This torque disrupts the symmetrical orbits of the gas, essentially robbing it of its angular momentum.
So the gas loses its spin.
Exactly. And without that rotational speed keeping it in orbit, the gas flows rapidly inward right toward the galactic center.
And here is the fascinating irony of the whole process. The black holes gorge on this inflowing gas and they light up. But that exact same material All that chaotic gas and dust funneling inward creates a thick, suffocating veil that hides the feast from our telescopes.
Right. The very act of feeding the black hole creates the dust that ensures we can't see it happening, which is why those hard X-rays are so vital. Though we should clarify a bit of nuance. Not every single merger activates both black holes simultaneously.
Oh, really?
Yeah, sometimes one lights up and the other stays dormant, depending on the exact dynamics of the gas flows. That makes our dual AGN Green Pea a rare and special catch. We caught both of them awake at the exact same time.
But that same veil of dust raises a completely different problem when we look at the very edges of the observable universe. Here's where it gets really interesting.
Yeah.
Let's travel back to the dawn of time.
Right, to the epoch of early galaxy formation.
The James Webb Space Telescope recently discovered these mysterious objects dubbed little red dots, which, sound harmless enough.
They do, but they've been causing quite a headache for astronomers. They are tiny red sources that exhibit incredibly broad spectral lines. Now, normally, broad lines indicate gas swirling around a supermassive black hole at tremendous speeds, but confusingly, these little red dots have extremely weak X-ray emission.
Right, and initially, based on the sheer width of those spectral lines, astronomers calculated that the black holes inside these objects were implausibly massive, like way too big for how young the universe was.
It was a massive crisis for our models. The math just didn't make any sense. They assumed the spectral lines were broadened entirely by gravity, gas orbiting the black hole at incredible velocities.
But the 2026 Nature paper proposed a groundbreaking new theory, right?
Yes. They pointed out that these young black holes are wrapped in exceptionally dense, thick, ionized cocoons of gas. We aren't just seeing light fly straight out from the accretion disk. That light has to navigate a gauntlet of free electrons.
Okay, so what happens when the light hits those electrons?
The photons undergo a process called electron scattering. They bounce off the free electrons in that superheated cocoon, and because those electrons possess their own extreme thermal energy, every collision transfers a tiny bit of momentum, slightly shifting the photon's wavelength.
Ah, I see. So the width of the light isn't caused solely by gas orbiting the black hole at tremendous speeds.
Exactly. That scattering effect stretches the light out. It produces much of the wide wings on the spectral lines.
So the gas cocoon is basically playing a trick on our telescopes.
Precisely. And when you mathematically correct the JWST data to account for this scattering effect, the inferred black hole masses shrink dramatically. They shrink by roughly a factor of 100.
100 times less massive. That is a huge difference.
It really is. Instead of being impossibly huge, they settle down into a much more reasonable range of about 10 to the 5 to 10 to the 7 solar masses.
Which puts them right back into the realm of the possible. So they are actually young black holes feeding voraciously, right near what physicists call the Eddington limit.
Yes, the Eddington limit.
I always picture the Eddington limit as this epic cosmic wrestling match. In one corner, you have the inward pull of the black hole's immense gravity, and in the other corner, you have the outward push of intense radiation pressure from all that hot, glowing gas.
That's a perfect analogy. The Eddington limit is the exact tipping point where those two forces are perfectly matched. Gravity pulling in equals radiation pushing out. These little red dots seem to be riding right on the edge of that limit.
Right. But we should probably note that science is an ongoing argument. This is still debated, isn't it?
Oh, absolutely. The true nature of the little red dots remains hotly debated in the astrophysics community. This scattering model is incredibly compelling, but it may not perfectly describe every single one of these objects. There's still a lot of work to be done.
So what does this all mean for you and me trying to understand the cosmos?
Yeah.
We have a nearby Green Pea galaxy, we have hidden mergers from 2018, and we have distant little red dots wrapped in scattering cocoons. How do we tie all this together?
Well, we unite them around a single question. Is the nearby Green Pea merger a readable echo of the exact conditions that helped black holes grow so rapidly in the early universe?
Because those distant little red dots, they're just too far away to resolve in comparable detail, right?
Yeah.
Even with JWST.
Exactly. But right here in our cosmic backyard, astronomers can cleanly separate the two Green Pea nuclei and study them across multiple wavelengths, X-rays, optical, infrared.
We can examine the crime scene up close?
Yes. Now, the systems are not perfectly identical. The universe was a different place back then. But the exciting possibility that unites them is the environment itself.
The compact, gas-rich stuff.
Right. Compact, gas-rich, low-metallicity environments, when combined with violent galaxy interactions, promote highly efficient black hole growth across all of cosmic time.
So the same physics applies, whether it's happening right next door or billions of years ago.
Precisely.
That is just incredible. But we should end with a sense of wonder, not false certainty here. Like you said earlier, this dual AGN is a pre-coalescence snapshot. We shouldn't predict they will collide tomorrow.
No, definitely not. It's a slow, unfolding dance that takes millions, sometimes billions of years.
But it leaves you with a rather provocative thought. Millions or billions of years from now, their eventual in-spiral will contribute to supermassive black hole mergers, and that will ripple the very fabric of space-time with low-frequency gravitational waves.
It's amazing to think about.
It really is. We started by pointing a telescope at a tiny green cosmic oddity. And by unpacking the physics, that little speck became a literal window into the universe's youth.
A window we are just beginning to look through.
If you enjoyed this cosmic mystery, please like the video and subscribe to the channel for more stories from the frontiers of science.